Hello everyone, and a warm welcome to the lecture series on the properties of solutions. As you may have heard it before, homogeneous mixtures are called solutions. When we think of solutions, we usually think of liquids. However, solutions can also be solids or gases. For example, the silver used in jewelry is a homogeneous mixture of about 7% copper and silver, making it a solid solution. The air we breathe is a homogeneous mixture of several gases, making air a gaseous solution. Nevertheless, since liquid solutions are the most common, we will predominantly focus on them in this module. We will particularly concentrate on aqueous solutions, which contain water as the solvent and either a gas, liquid, or solid as the solute. Accordingly, we will start by examining how intermolecular forces influence the physical properties of liquids. We will then consider what happens at the molecular level when a substance dissolves, paying particular attention to the role of intermolecular forces. Then we will study the major factors affecting solubility, focusing on the nature of solute-solvent interactions. You will see that some physical properties of solutions depend only on concentration and not on the identity of the solute. We will examine colligative properties, including the extent to which the solute lowers the vapor pressure, increases the boiling point, and decreases the freezing point of the solvent. Finally, we will discuss the osmotic pressure of a solution, which is another colligative property. In the previous module, you learned that the molecules in liquids are held together by intermolecular forces, which are based on electrostatic attractions between opposite charges or partial charges. Intermolecular forces acting between atoms or molecules in a pure substance are also known as van der Waals forces and include dipole-dipole interactions and London dispersion forces. You learned that dipole-dipole interactions exist between polar molecules, whereas nonpolar molecules are held together by dispersion forces alone, which are formed between instantaneous dipoles and induced dipoles. When a nonpolar molecule acquires an instantaneous dipole, it is said to be polarized. In general, dispersion forces act between all molecules, both nonpolar and polar. We also discussed hydrogen bonding, which is an especially strong dipole-dipole interaction that occurs in molecules containing NH, OH, or FH bonds. It should not surprise you to learn that several of the physical properties of a liquid depend on the magnitude of its intermolecular forces. In this lecture, we are going to learn about 3 such properties, including surface tension, viscosity, and vapor pressure. The surface of water behaves almost as if it has an elastic skin, as evidenced by the ability of certain insects to walk on water. This behavior is caused by an imbalance of intermolecular forces at the surface of the liquid. As the figure demonstrates, a molecule within a liquid is pulled in all directions by the intermolecular forces between it and the surrounding molecules, resulting in no net pull in any one direction. Similarly, a molecule at the surface of a liquid is pulled downward and sideways by neighboring molecules, but as you can see here, there is no upward pull to balance the downward or inward pulls into the bulk of the liquid. This imbalance results in a net inward pull on the molecules of the surface, causing the surface of a liquid to tighten like an elastic film, thereby minimizing its surface area. For instance, the beating of water on the leaves of plants, as shown here, is another illustration for this phenomenon. A quantitative measure of the elastic force at the surface of a liquid is called surface tension, which is defined as the amount of energy required to stretch or increase the surface of a liquid by a unit area. A liquid with strong intermolecular forces has a high surface tension. For example, water, with its strong hydrogen bonds, has a very high surface tension. Yet another illustration of surface tension is the meniscus, the curved surface of a liquid contained in a narrow tube. The figure shows the concave surface of water in a graduated cylinder. This shape is induced by a thin film of water adhering to the wall of the glass cylinder. Here, the surface tension of water causes this film to contract and as it does, it pulls the water up the cylinder. This effect, known as capillary action, is more pronounced in a cylinder with a very small diameter, such as a capillary tube used to draw a small amount of blood. There are two types of forces that bring about the capillary action. One is cohesion, the attraction between similar molecules, in this case, between water molecules. The other is adhesion, the attraction between unlike molecules, in this case, between water molecules and the molecules that make up the interior surface of the graduated cylinder. If adhesion is stronger than cohesion, as demonstrated here for water, the content of the tube will be pulled upward. However, the upward movement is limited by the weight of the liquid in the tube. In the case of mercury, shown in the figure on the right, the cohesive forces are stronger than the adhesive forces, resulting in a convex meniscus in which the liquid level at the glass wall is lower than that in the middle. Another property determined by the magnitude of intermolecular forces in a liquid is viscosity, which measures a fluid's resistance to flow. When intermolecular forces are strong, the liquid will have a high viscosity, meaning it flows more slowly. Typically, the viscosity of a liquid decreases with increasing temperature, as higher temperatures increase the speed of molecular movements, thereby weakening intermolecular forces. The phrase slow as molasses in winter refers to the fact that molasses pours more slowly in cold weather. That is, it has a higher viscosity. You may have noticed that honey and maple syrup become thinner when heated. This happens due to the weakening of intermolecular forces. In general, liquids with strong intermolecular forces have higher viscosities than those with weaker intermolecular forces. For instance, in honey, there are multiple strong hydrogen bonds between the molecules of fructose, the major constituent of honey. The following table lists the viscosities of some liquids that may be familiar to you. For example, water's high viscosity, like its high surface tension, is the result of hydrogen bonding. Now, note how large the viscosity of glycerol is compared to the other liquids listed in the table. Glycerol is a sweet-tasting, syrupy liquid used for a wide variety of purposes, including the manufacture of candy and antibiotics. Its structure is similar to that of water and is presented on the right. So, each glycerol molecule has 3 OH groups that can participate in hydrogen bonding with other glycerol molecules. Furthermore, because of their shape, glycerol molecules have a strong tendency to become entangled rather than slip past one another as the molecules of less viscous liquids do. Altogether, these interactions contribute to its high viscosity. The last topic we should touch upon here is vapor pressure. You may have encountered the term vapor pressure during physics from high school. In fact, vapor pressure is another property of liquids that depends on the magnitude of intermolecular forces. Substances that have high vapor pressures at room temperature are said to be volatile. The molecules in a liquid are in constant motion, and like the molecules in a gas, they have a distribution of kinetic energies. The most probable kinetic energy for molecules in a sample of liquid increases with increasing temperature, as shown in this figure. If a molecule at the surface of a liquid has sufficient kinetic energy, it can escape from the liquid phase into the gas phase. This phenomenon is known as evaporation or vaporization. For instance, consider the apparatus shown here. As a liquid begins to evaporate, molecules leave the liquid phase and enter the gas phase in the space above the liquid. Molecules in the gas phase can also return to the liquid phase if they strike the liquid surface and become trapped by intermolecular forces. The reverse process to evaporation is known as condensation. Initially, evaporation occurs more rapidly than condensation. However, as the number of molecules in the gas phase increases, so does the rate of condensation. The vapor pressure over a liquid increases until the rate of condensation equals the rate of evaporation. remaining constant at a given temperature. This state, or any situation in which a forward process and a reverse process occur at the same rate, is called dynamic equilibrium. Although both processes continue, the number of molecules in the gas phase does not change over time, meaning equilibrium has been reached. The pressure exerted by the molecules that escape to the gas phase, once it stops increasing, is called the equilibrium vapor pressure, or simply the vapor pressure. In liquids with strong intermolecular forces, the kinetic energy of the molecules is lower, causing them to move more slowly and reducing their likelihood of leaving the liquid phase. Consequently, liquids with strong intermolecular forces have a lower vapor pressure compared to those with weak intermolecular forces. This, of course, is true only when comparing liquids under identical conditions. Again, if we go back to these graphs, you see that the average kinetic energy of molecules in a liquid increases with increasing temperature. Therefore, at a higher temperature, a greater percentage of molecules at the liquid surface will possess sufficient kinetic energy to escape into the gas phase. Consequently, the vapor pressure of liquids increases with increasing temperature. To sum up, in this lecture, you were introduced to some of the most important properties of liquids, including surface tension, viscosity, and vapor pressure. You now know that surface tension is the net inward pull on molecules at the surface of a liquid. Surface tension is related to phenomena like cohesion, which refers to the attractive forces between molecules within a substance, and adhesion, which refers to the attractive forces between molecules in a substance and their container. You saw that the balance between cohesion and adhesion determines whether a liquid meniscus is concave or convex. It also gives rise to capillary action, in which liquid is drawn upward into a narrow tube against gravity. We discussed viscosity, which is the resistance to flow, reflecting how easily molecules move past one another. Then we focused on evaporation, also known as vaporization, which is the phase change from liquid to vapor. The reverse process is called condensation, the phase change from vapor to liquid. In a closed system, when vaporization and condensation occur at the same rate, a state of dynamic equilibrium exists, and the vapor pressure equals the equilibrium vapor pressure. Vapor pressure measures how easily molecules escape to the vapor phase. For instance, a volatile substance has a high vapor pressure. In the following lecture, I will introduce you to the main types of solutions. Thank you for your attention.